All right, lads and ladies, welcome back. Today, we are going to kind of polish up the material we've been discussing lately on calculus operations with parametric curves by giving the more complete story around Arclength and giving a more complete story around surface area. So with Arclength, I do want to talk a tiny little bit about something that I'm not going to test you on. I don't do that a lot, but there's a little bit of content related to Arclength that is so important to mathematics that your textbook doesn't discuss in this section, that I cannot resist just sharing the smallest bit of it with you. So we're going to do that, and then we're going to do some surface area calculations. After we do the surface area calculations, if there's time, I will introduce the material that we're going to be moving into, which is polar coordinates. So let's go ahead and get started. We have quite a full day here. There we go. Oh, this is pretty cool, by the way. I've been spending all of my free time lately working on a bot to trade Bitcoin. And this is something I did not realize was accessible to everyday people, but you can do this too if you are at all comfortable working in Linux, and it's super simple. You can set up a computer program that will automatically make cryptocurrency trades for you at optimal times. It seems like a money printer if you're able to come up with a good strategy. Trade is the open source one that I've been playing with, and it's very easy to set up, and then you just have to be a genius and come up with a really good trading strategy. But I think that's probably not the part. Anyway, this is MAC2312 section number 004, which is a Calc 2 class, and the date today is the 13th of April. So the 13th of April 2022. Today, as promised, we're going to talk a little bit more on Arclength. So I just want to get some practice doing computations, and then talk with you a tiny bit about reparametrizing a curve with respect to Arclength, because that is very cool. We're going to talk about surface area. And then we might introduce polar coordinates. So that's the plan. Let's go ahead and dig in. So Arclength, what was Arclength? I'll begin by saying here, recall that if the parametric equations x equals x of t, y equals y of t, trace a curve as t runs from A to B, then the length of that curve is given by the following integral. It would be the integral from t equals A to t equals B of the square root of dx dt squared plus dy dt squared. And the integral is done dt. So last time we proved this formula and we did a little bit of calculation. Today I want to do a little more calculation and then show you one cool thing that can be done with this, even though it's not, strictly speaking, something that I'm going to test you on. Moving ahead, your textbook calls Arclength L, which is a terrible disservice because everyone else in the universe calls it S. So what I'm going to do, I'm going to call this S, lowercase s for Arclength. And the thing that you integrate to get the Arclength, this square root times dt, we're going to call that ds. And this will be important as we talk about surface area, right? So like with volume, you integrate dv to get v. With arc length, you integrate ds to get s. And s is the length of the curve. I don't know why s is the symbol that's used. L in English might make more sense for us, but historically, everywhere in this little field of mathematics called differential geometry, we've always used s for arc length. So let's do one more example. I think we got one or two of these under our belt the other day, but I think it would be wise to look at least one more. There was one that was kind of fun. Yeah, number 42 here is nice. So we want to find the length of the curve given by x equals e to the t minus t, y equals 4e to the t over 2. So let's go ahead and write that down. And we're told t here is going to run from 0 to 2. Okay. According to the formula above, I just need to compute this integral, which means I need to calculate so this is y equals y of t, and the word here is trace, T-R-A-C-E. According to the formula above, I just need to do this integral, which means I need dx dt and dy dt, which are the regular derivatives, t time derivatives of this thing, and the derivative of this thing. So let's calculate dx dt. The derivative of e to the t minus t is e to the t minus 1. Blue pen is dying. I'll switch to purple. That's usually how we do our work for examples anyway. So dx dt, the derivative of the x function, is the derivative of e to the t minus t, and that is e to the t minus 1. dy dt is the derivative of 4 times e to the t over 2. Well, that's 4 times e to the t over 2 times the derivative of t over 2, right? It's a chain rule thing. And the derivative of t over 2 is 1/2. So the 4 and the 1/2, you can multiply these, you get 2e to the t over 2, like so, by the chain rule. Alrighty. So now I can set up my integral. My arc length is the integral from t equals a, which is 0, to t equals b, which is 2, of the square root of dx dt squared, that's e to the t minus 1 all squared, plus dy dt squared, that's 2e to the t over 2 squared, and the integral is done dt. Remember, the square root cannot be given to those two pieces separately because there's addition separating them. So the only thing we can do is like FOIL this out, figure out what this is, combine like terms, and hope that we can do something with that. So let's go ahead and see what we get when we multiply that stuff out. I still have my square root. When you FOIL out e to the t minus 1, you get e to the t times e to the t, which is e to the 2t, minus 2 copies of e to the t. And then -1 times -1 is +1. When I square 2e to the t over 2, I'm going to get 2 squared, which is 4, times e to the 2t over 2, which is just e to the t. So that's going to be 4e to the t. All of this is under my square root, and we still have our dt at the end. I have two like terms here. This and this are like terms. So when I put those together, I'll have the integral from 0 to 2 of the square root of e to the 2t minus 2e to the t plus 4e to the t is plus 2e to the t. And then the +1 is still hanging out. I mentioned the other day that from time to time when solving these problems, you'll need to lean on some factoring tricks that you may have learned in pre-calculus or college algebra. This is one of those places. I would say it is nice to recall that e to the 2t is the same as e to the t squared. So e to the 2t plus 2e to the t plus 1 is the same as e to the t squared plus 2e to the t plus 1. In fact, that's where that e to the 2t came from. And then you can factor this. If you think of this as like u squared plus 2u plus 1. I'm not doing a u sub in the integral. I'm just thinking about how to factor this. This factors as u plus 1 all squared. So e to the 2t plus 2e to the t plus 1 is e to the t plus 1 all squared. Some people like to do this factoring in their heads, just looking at this, but I'm writing this here just so you can see where it's coming from. So the thing under the square root factors nicely, which means my integral becomes the integral from 0 to 2 of the square root of e to the t plus 1 all squared dt. And the reason why this is nice, of course, is that the square root is going to go away. That square root is what makes these arc length integrals so challenging. And by factoring the thing under the square root as a perfect square, we are able to get rid of that square root, which will give me the integral from 0 to 2 of just good old-fashioned e to the t plus 1 dt. Okay, great. Now we can calculate our antiderivative. That's going to be e to the t plus t. The integral of e to the t dt is e to the t. Integral of 1 dt is t. And I evaluate this from 0 to 2. And when I plug in my upper bound, I get e squared plus 2. When I plug in my lower bound, I get e to the 0, which is 1 plus 0. So this is e squared plus 2 minus 1, which is e squared plus 1. And that indeed is the length of this curve. I just got a question about exam 3. So exam 3 is scheduled for the last day of class. So it's not this Friday, but next Friday. We build in that extra time in the syllabus so that we can spend a little bit more time on other topics. And we ended up spending that little bit of extra time on power series. Yes, the 22nd. Ooh. He's going to have to wait. All right. So this is the arc length of that curve. right? Nothing too crazy. This integral was not out of control hard, although we did see some the other day that can get pretty out of control hard. This one was not bad. Before we pivot, any questions on this calculation? Okay, before we pivot to going back to talking about surface areas, I do want to just share one important idea with you. And that is what's called parametrizing with respect to arc length. The basic idea is this. Let me go into Desmos and let's look at that curve we were just playing with, e to the t minus t for e to the t over 2. And I'll let t run from like 0 to 3 or something. Maybe negative 2 to 2, just for fun. Something like this. Okay, here's my curve. And I can watch a little particle moving along this curve. If I replace these with some other variable, then I can give us a moving particle here. Let's do it. So it's going to move from -2 to 2. Swap size, we'll say 0.1. We'll do it just in the forward direction. Maybe we'll even step 0.01. I want to draw your attention to how fast the particle is moving. Right down here, it starts off very slow. And as we fly out there, it starts going faster and faster and faster. And if I give us a little bit more space to fly out there, you'll see it speeding up more still as we zoom, as we go out along this curve, right? Starts off slow, but then quickly picks up speed and starts flying like a really quick bastard. Smooth it out a little. One really important idea from differential geometry, which is the field of mathematics that we're just shaving the very surface off of right now, is the idea of walking a curve at a constant speed. You see all of these parametric curves we've been looking at, we haven't been paying attention to how fast we traverse them. It would be nice if there was some way for me to rewrite the parametric equations so that we walk along the curve at a constant speed. Now, for this particular example, it's very hard to come up with a formula to do that, but I just want to give you the idea as to how you would do that. If we could find a function call it s of t, such that s of t is the length of the curve from t equals a to t equals t. we could rewrite the parametric equations in terms of the variable S in such a way that the curve is traversed, or yeah, at speed 1. There's a picture here, so I'm going to describe this as well as I can. And I won't make you do any calculations, but I do want you to think along with me just a tiny bit. So maybe here's my initial point. Maybe here's my terminal point. And what I'm after is a function that will give me you pick your favorite arbitrary t value, over here, the initial point comes from t equals 0. I want a function that gives me this length. As a function of t, right? Just the piece that I've like traced over there in the blue pen, the green pen. Suppose we find the function maybe I'll call it s equals, instead of s of t, so I don't overuse the variable, s equals L of t for length. So s of, when t is 0, it's the length, it's 0. When t is 1, it's however far you've walked in 1 second. When t is 2, it's however far you've walked in 2 seconds. When t is 3, it's however far you've walked in 3 seconds. Then we could solve for t, and we would get L inverse of s equals t, and plug that into our parametric equations. So x equals x of t would become x of L inverse of t, which, I'm sorry, x L inverse of s, not t here. That's, and y, which is y of t, would be y of L inverse of s. These new parametric equations, this and this, would trace the same curve, but at a constant speed. So if this were a slightly more advanced class, I would do some of these calculations for you, and we would work through some problems, and they would be on your test. I don't want to overwhelm you, and unfortunately your textbook doesn't actually have this in it. I don't know why, it's kind of tragic, but this idea of calculating the arc length as a function, which would be, the function that returns the length of the curve up to a certain t value, rather than using a constant here or getting the whole length of the curve. We want something where I can plug in t values and get the length up to that t value. If you find such a function, then you could solve it for t and plug that into the original parametric equations. And that would give you a new set of parametric equations tracing the same curve, but walking at speed 1. Okay. After the word curve, but traced at a constant speed. So I just wanted to open your eyes to this as a possibility. Is traversed at speed 1. This is something you will definitely see in Calc 3. Definitely, if you have any sort of reasonable Calc 3 class, you will be calculating arc length parameters there. And I used to do it in Calc 2 when we had a different book, but not doing it now. So I just want to share the idea with you. Okay. What I want to do now is just practice some surface area calculations. I'll remind you the formula we got for surface area last time, where it came from, and we'll look at a variation on that formula, and then we'll do some calculations with both. Here we go. Given a parametric curve, x equals x of t, y equals y of t, with a less than or equal to t, less than or equal to b, we can generate a surface by rotating the curve around an axis. So this is very, very similar to what we were doing with volumes at the start of the class, at least as far as the geometry is concerned. If my parametric curve looks something like this, and I rotate that about the x-axis, then that will create a solid looking something like, or sorry, a surface looking something like this. And in order to find the arc length, or sorry, in order to find the surface area of this 3D surface, what we would do is take a little unit of arc length here, which we call ds, right? Like s is arc length, ds is a tiny differential piece of arc length. Over here, that corresponds to a little band. Right? When you rotate just this little segment of arc length, you get this little band of surface area. It's kind of like the little slices of volume that we had back in the volume sections, only instead of a volume, it's a surface area, because instead of taking a little area, a little strip, and rotating it, which would generate a little volume, I'm taking a little line segment and rotating it, and that's going to generate just this little band of surface area. The area of that band the surface area of the tiny band, I will call dA, A for area, D for tiny. And we can think of, remember how we did this, we think of it like a watch band. You take it off and you lay it out flat. This side length here is ds. This side length here would be the circumference, which is 2 pi times the radius. And the radius is this distance over here. So if we're rotating about the x-axis, the radius would be y, or y of t. My circumference is going to be 2 pi r, and r is y of t, so it's 2 pi times y of t. Which means that my little bit of surface area here, the area of this tiny little band, is going to be this width times this height, which is going to be 2 pi times y of t times ds. Where ds is the thing that you integrate to get the arc length. ds, remember what we said at the start of class, is the square root of dx dt squared plus dy dt squared dt. So plugging all this in and integrating from my initial point over here, where t is equal to a, to my terminal point over here, where t is equal to b, I get that the area, the surface area, would be the integral from t equals a to t equals b of the little surface area, which is the integral from a to b of 2 pi times y of t times ds, and ds is this thing, the square root of dx dt squared plus dy dt squared all done dt. So this is one formula for surface area. This is if you're rotating about the x-axis. I'm going to briefly walk you through what happens if we rotate about the y-axis, and then we'll do some calculations. Don't worry, I will summarize the formulas for you before we get into the calculation. So this is about the x-axis. And over here, I'll do this about the y-axis. Same vibe. We'll start with a parametric curve. Here's my x-axis, here's my y-axis. Maybe my initial point is over here. And I just do something like this, keeping it simple for the purposes of the picture. So initial point at the bottom, terminal point at the top. And I want to rotate this solid, or this curve about the y-axis. That's going to generate a surface looking like this piece, this distance doubled. So it looks something like this, with a little open circular base here and the top here. And if I wanted to find the area, the surface area for this surface, I do the same thing. I give myself a little segment of arc length along the original curve. Right, this little segment here, which we call ds. That little segment in this picture is here, and it will correspond to a little band of arc length. Sorry, a little band of surface area, not a little band of arc length. A little piece of arc length, when rotated, gives us a little band of surface area. Like so. Same deal, we're going to kind of unroll the band. The small dimension here is ds. This pen is dying. Small dimension here is ds, and the long dimension here is the circumference of the band. Which is 2 pi r, and in this case, r is a horizontal distance. R would be this distance, which is x. So the circumference there is 2 pi times x of t. Oh, is this one dying too? Yeah. So here, dA would be 2 pi times x of t times ds. ds is still the same thing because the arc length formula here doesn't change from the arc length formula up here. So ds would still be that square root of dx dt squared plus dy dt squared dt. So the surface area here would be the integral from time t equals a to t equals b of the little piece of surface area. Right? So thinking of my total surface is made up of a bunch of these tiny little bands. And that dA, I get integral a to b, is 2 pi x of t times ds, and ds is this big square root. All right, so those are our two formulas for surface area. And there's a bunch of different ways you could write these down. I will give you on the next page a simple, I'll show you how I remember them. But you may want to put these in your notes, right? This is surface area when revolving a parametric curve around the x-axis. This is the surface area when revolving a parametric curve around the y-axis. The only difference is this piece, which comes from the radius, right? The radius. If you're revolving around the x-axis, your radius is y. If you're revolving around the y-axis, your radius is x. And because these are parametric curves, I'm writing y of t to remind us this is a function of t. It's the y function. I'm writing x of t here to remind us that this is a function of t. It is the x function. Okay. So in summary, here's how I remember surface area formula. If we're revolving about the x-axis, I think of the surface area as being the integral from t equals a to t equals b of 2 pi y ds. And if we're revolving about the y-axis, then the surface area is the integral from a to b. Again, those are t values of 2 pi x ds. And the thing that you have to remember here is where x is x of t, it's your x function. Y is y of t, it's your y function. And ds is your little element of arc length, the square root of dx dt squared plus dy dt squared times dt. So this is how I remember these, right? I think these formulas are short and sweet, nothing too complicated. And there's only two of them. There's one for revolving around the x, there's one for revolving around the y. I'll hold here for a minute, make sure everybody gets this written down nice and clean. You might want to add here that a is less than t, is less than b. Those are the t values, the time domain. I can go back in just a second. I just want to hold here for a minute, make sure everybody gets a chance to write this down. And then if we want to go back to get some of the pictures or something like that, I can do that. So I'll hold here for another, say, 5 seconds. Now let's do 10. All right. And I can go back for a second. You want to capture any of these pictures or the derivation of the formulas. this is where those are coming from. Okay, I'll hang out here for another 10 seconds. And then we're going to do some examples. All right. Example time. The textbook has some fun ones here. Let's see. Surface area. Yeah, we can do. Oh, and they've got this one as well. All right. We can find the surface area for, let's see, find surface area generated by rotating about the y-axis. Let's start with an x-axis one. Let's do x equals t squared, x equals t cubed, y equals t squared, and t goes from 0 to 1. All right. I think just for fun, it would be worthwhile to try and sketch this parametric curve. We haven't actually done a sketch of a set of parametric equations in a few meetings, so let's do that. That'll give us an idea of the picture we're looking at, and then we'll calculate the surface area associated with that surface. So first, let's sketch the surface. To do that, I need to sketch the parametric curve. Since x is t cubed, we know that x to the 1/3 is equal to t. Solving that for t. We have y equals t squared, which would be x to the 1/3 squared, right? Because t is x to the 1/3, i.e. y is x to the 1/3 squared is x to the 2/3. And you may remember what the graph of x to the 2/3 looks like. This is a curve that shows up in Calc 1. It is this cusp form, looking kind of like the square root function in quadrant 1, and then it's an even function. So we have this symmetry, and there's this pointy bit down here called a cusp. Since t is running from 0 to 1, and both x and y are straight up power functions of t, that means we're looking at the portion of this graph that goes from 0, 0 to, I'll call this 1, 1 here. So the part that I am bolding is our parametric curve. T equals 0 down here, t equals 1, this point up here. And our orientation is like this. So if I were going to revolve this curve around the x-axis, then the solid I would get will look something like this. It's a bowl, like that. So what I'm trying to find is the surface area for this bowl. I'm trying to say solid, the surface looks like this. So then to compute that surface area, I know that I need dx dt and dy dt. I know I need to calculate the ds thing. So calculating, I cannot spell today, calc the surface area. Requires dx dt. That's a part of my formula. So if I take this x function and I differentiate it, I'm going to get 3t squared. I also need dy dt. So if I take this y function and I differentiate with respect to t, I just get 2t. And that means that my surface area is going to be the integral from a to b, from 0 to 1, of 2 pi. Now I'm revolving around the x-axis, so my radius is y, y of t, and then I've got the square root of dx dt squared plus dy dt squared dt. So let's go, let's do it. The 2 pi can come out, it is a constant. The reason I like to write y of t instead of just y is to make sure you understand that this is not a constant. The x and the y in those surface area formulas never pop out of the integral. They are not constants. They are functions of t, and the integral is done dt. So this piece cannot come out of the integral. Y here is just t squared. The square root of dx dt squared, well, dx dt, where is it, is 3t squared. So this is going to be 3t squared plus dy dt is 2t, so that's 2t squared. And we're doing this dt. And this integral is not as bad as it looks. Let's clean it up a little bit and see what we can do. I have here now 2 pi times the integral from 0 to 1 of t squared times the square root of 3t squared all squared. That's 9t to the 4. 2t all squared is 4t squared. dt is just dt. Now, it's been a while since I really put you guys through any challenging integrals, so I want you to help me out. What can I do here? Excellent. Yeah, I can factor a t all the way out from the square root, because inside the square root, I can factor a t squared. Sorry, this is my wife. Sorry about that. Yeah, we're going to factor out. So the way I'm going to do this, we'll factor out a t squared under the radical, and then we'll see what we can do with that. So I've got my 0 to 1. I've got my t squared out front. And then inside the radical, I'm going to factor out a t squared. So this will be 9t squared plus 4 times t squared, all under that radical. And now that this t squared is multiplying this, now that I've factored it out, I can take the square root of him separately. He can pop out of that square root. So this is 2 pi times the integral from 0 to 1 of t squared times the square root of 9t squared plus 4. And now outside the squared, I have this t dt. And it's true, you could multiply this t squared and this t together, but I'm writing it like this to help us see something we can do. Excellent. Yeah, so the suggestion here in the DM was a substitution. Does anybody see what I could sub for? I don't think subbing z equals 18t would work. Yeah, because if you sub z equals 18t, then dz is just going to be 18 dt. So yeah, it is true that I've written this t over here because this is going to be a part of some dz. But if my differential is going to be t dt or something like that, then yes, exactly. Then I want to substitute for some quadratic. And you can do this with multiple u subs or z subs. But the quick way to do this, I think the smart way to do this is to make the substitution for the radicand, z equals 9t squared plus 4. And then dz would be 18t dt. I'll show you why this works so well in just a second. We need to change our bounds. So our old bounds were t values going from 0 to 1. When t is equal to 0, if I plug 0 in for t here, I get 9 times 0 squared plus 4. So my z value will be 4. When t is 0, z is 4. And when t is equal to 1 here, I'll have just 9 times 1 plus 4 is 13. So z is going to be 13. So let's plug in the pieces we see right away. I've got 2 pi integral from 4 to 13. I'm going to leave space here. So we're going to worry about the t squared in just a second. We'll take care of everything else first. The square root of 9t squared plus 4, that's the square root of z, right? Because that's what I'm subbing for. T dt, that's 1/18 dz. All right, just divide this dz equals 18t dt, divide both sides by 18, you get t dt and 1/18 dz as being equal. So the t dt is going to be 1/18 dz. And the question is, what do I do with this t squared here? This piece is still left over. This becomes the square root of z. This becomes 1/18 dz. What can I do with this? Excellent. I go back to my substitution here, and I solve it for t, or for t squared. So that means z minus 4 would be 9t squared, which means 1/9 z minus 4 is t squared, and this is coming from here. So this piece will be 1/9 z minus 4. And that is the substitution. It's a clever one. It's quite similar to some substitutions we did at the start of the semester, like when integrating x times the square root of x minus 3 or something, you sub for x minus 3. Then to fix that x, you had to say, okay, well, that would be z plus 3. Same sort of thing. Same sort of thing. So if you're a little rusty on your u sub, or if you're a little rusty on trig sub, right, this could have easily become a trig sub problem. Make sure you practice that stuff. In other words, don't Mathway or Symbol Lab your way through this homework. Okay, that will only hurt you. I think I told you guys, I caught a few people cheating with Mathway on the last test. Don't let that happen. So really practice this stuff. It is possible to get good at this. It's not impossible. Okay, I've got a 1/9 here and a 1/18 here. I'm going to move those out. I'll just write 9 times 18 downstairs, out front. What's left is the integral from 4 to 13 of z minus 4 times the square root of z, I'll write as z to the 1/2 dz. Two and the 18 can talk to each other, right? You can cancel a factor of 2 from this and you get 9. So this is going to become pi over 81, pi over 9 times 9. And then within my integral 4 to 13, I'll distribute. So that's z to the 1 times z to the 1/2, which is z to the 3/2, minus 4 times z to the 1/2. DC still chilling. And now it's a power rule thing. An antiderivative for z to the 3/2, well, you add 1 to that power, that's 5/2. So it's going to be 2/5 z to the 5/2, right? Add 1 to the power, divide by the new power. We've seen so much of this. And then minus 4 times, if I add 1 to 1/2, I get 3/2. So that's going to be 2/3 z to the 3/2. And remember, one of the reasons it's so nice to change your bounds is that you don't have to plug back in for the original variable. You just evaluate this between the new bounds. So I've got my pi over 81 out front. And then here I'll have 2/5 times 13 to the 5/2 minus 4 times 2 is 8/3 times 13 to the 3/2. That's what I get when I plug in my upper bound. Minus, plug in my lower bound, I'm going to have 2/5 times 4 to the 5/2 minus 8/3 times 4 to the 3/2. And there is some cleaning up that could be done with the numbers, like 4 to the 5/2, that's actually an integer, that's 32. 4 to the 3/2 is 8. So if you wanted to, you could clean this up a tiny bit, but I don't really care. At this point, I am happy. Let's make a little note here. We could simplify a bit. We could simplify 4 to the 5 halves as 2 to the 5, which is 32. And 4 to the 3 halves is the same as 2 cubed, which is 8. So each of these pieces could be cleaned up just a little bit. But on a test or something, this purple line would be a perfectly good place to stop. Okay. Fairly involved problem. Let's take a minute and make sure you're comfortable with it. What do we want to know? Any questions at all from any part of this? This is everything after the Z sub. Here's everything before the Z sub. Okay. We have only about 5 minutes left, which is probably not enough time to do a full second calculation, but let's at least set up an integral for one of these done revolving around the y-axis. Here we have very similar curves. Let's do 66. So it's the same curve we found the arc length of earlier. Let me just write this down. Find the surface area for x of t equals e to the t minus t, y of t equals 4e to the t over 2, where 0 is less than t less than 1, about the y-axis. We know we're going to need this formula. The surface area about the y-axis is the integral from t equals a to t equals b of 2 pi times x of t times ds. And I'm going to cheat here a little bit. We calculated ds for this function, or for this curve earlier. ds is the square root of dx dt squared plus dy dt squared dt. And earlier when we did this, we got e to the t plus 1 dt from our earlier example. All right, where is that? Here. Right. Earlier here, we were able to simplify the dx dt squared plus dy dt squared and get this. So here, we're going to be integrating from 0 to 1, 2 pi my x of t function, which is e to the t minus t, times ds, which is e to the t plus 1 dt. The 2 pi comes out, and I'm left with the integral from 0 to 1 of this thing, which I can FOIL out. That's e to the t times e to the t, which is e to the 2t plus e to the t minus t e to the t minus t. I'm going to split this into super easy part and somewhat less easy part. Let's take the e to the 2t plus e to the t and the minus t. And then subtract from that because it's negative. 2 pi integral 0 to 1 t e to the t dt. Okay. This first piece, I grouped those 3 terms together because none of these require anything too fancy. The e to the 2t is a little micro u sub. E to the t, of course, will anti-differentiate to e to the t. And the t itself is a power rule thing. So my antiderivative here is 1/2 e to the 2t plus e to the t minus 1/2 t squared, and that will be evaluated from 0 to 1. This piece I need to do separately. This is, I'll just do the indefinite integral of t e to the t dt real quick. This is done using IBP, where u is t and dv is e to the t, which means du would be dt, and e to the t dt, v would be e to the t. So according to my IBP formula, this would be t e to the t minus the integral of e to the t dt, which is t e to the t minus e to the t. And yeah, we would have a plus c here, but I'm doing this as side work. So I'll have minus 2 pi times this thing, t e to the t minus e to the t evaluated from 0 to 1. I can put these pieces back together now, and that's worth doing because this e to the t and this e to the t will cancel. So that's going to be 2 pi times 1/2 e to the 2t minus t e to the t minus 1/2 t squared from 0 to 1. And you may want to highlight what we're doing here. I'm putting this guy. Oh wait, minus is going to make plus. Oh, nope, I take it back. I take it back. I take it back. We should not do that. That's not how that comes out. We are going to put those together, but what we get is slightly different. So what I've got here is 2 pi times 1/2 e to the 2t, e to the t minus negative e to the t is going to be plus 2 e to the t. And then we have minus 1/2 t squared and minus t e to the t, all evaluated from 0 to 1. That's the correct way to do this. So now finally we can evaluate at our upper bound. I'll have 1/2 e squared plus 2e minus 1/2, and then minus 1 times e to the 1 is minus e. And from that, I subtract what I get at my lower bound, which is 1/2 times e to the 0, which is just 1/2, plus 2e to the 0, which is just 2, minus 1/2 times 0 squared, which is 0, minus 0 times e to the 0, which is also 0. So all together here, I've got a 1/2 e squared, no other e squared. I've got 2e minus e. So I can put this and this together. I can put this and this and this together. So that would be 2 pi times 1/2 e squared plus 2e minus 1e is just plus 1e, minus 1/2 minus another 1/2 is minus 1, minus 1 plus 2 is plus 1. And that is the surface area. Now this problem was fairly quick, but a lot of the work we were getting from that previous example, right? Simplifying the square root of dx dt squared plus dy dt squared. That's a big part of the problem. So all of these, arc length, surface area, they are fairly involved, right? All of these lead to integrals which sometimes require trig sub, sometimes require u sub, sometimes require careful algebra. Sometimes, like we saw here, requires some integration by parts. All of the stuff that we learned at the beginning of the semester, with the possible exception of partial fractions, becomes relevant here. And I take it back. Partial fractions could show up here too. You know, get in the right situation, you could involve partial fractions. Practice these problems. If you're having trouble with them, come to office hours. Exam 3 is going to be on the 22nd. And it is going to include this stuff. It is going to include arc length and surface area in the same spirit that exam 1 involved volume problems. So make sure you're ready to do this shit. That is it for me. Are there any burning questions from you guys before I close the meeting? Alrighty, then I'll go ahead and wrap it up here. On Friday, we're going to introduce polar coordinates, and we'll learn how to graph functions in polar coordinates, all that good stuff, so that next week we can learn how to do calculus operations with polar coordinates, and that will be the last bit of material in the course. So please work hard. If you need help, please ask for help. I'm here. I'm happy to help. Otherwise, I will see you guys on Friday. Take care.